Good afternoon, everyone, and welcome to our second webinar in the series, where you will explore how to overcome your optical system challenges with Ansys Speos. First, let me introduce myself. My name is Lisa Sitar. I'm a marketing officer at Infinite Simulation Systems and a moderator of this webinar. But before we officially start, I would kindly ask to wait just 1 or maybe 2 more minutes for everyone else to join, and then we will proceed. Okay, let's begin. First, short instructions on the webinar tool you're currently using. As you can see, you have more different options. Bottom left, you can react during the session. Top right, you have two important buttons. One is the setting button and another one is a question tab. Here, one very important remark. You cannot unmute yourself during the webinar, but you're very welcome to ask a question if you have any. So please, in that case, do not try to raise your hand or unmute yourself, but just write your question down under the question tab you see, and all the answers will be provided after the webinar. Please also know that this webinar is being recorded and the recording will be shared with you together with the presentation slides afterwards. So today I'm joined by application engineer Ekim, who is my colleague and who will tell you more about how to use Ansys simulation tools in order to overcome your optical system challenges. But first, for those that might not know us yet, just a very, very short introduction of Infinite. So who are we? We are an Ansys Elite channel partner serving Benelux region and having more than 30 years of experience in computer-aided engineering. We are based in Breda in the Netherlands and Leuven in Belgium. And our expertise spans a broad range of simulation domains like mechanics, fluids, electronics, photonics, and more, allowing us to support clients across various industries. Our main mission is to improve your design efficiency, accelerate your time to market, help you reduce the need for costly physical prototypes, and of course, enabling smarter and faster product development. But that's not all. We also offer expert support, consultancy, and we even organize trainings which are basically tailored to your needs, where you can learn in practice how to use Ansys simulation tools and then apply them to your engineering challenges. So for now, that's everything from me. I will slowly give my word to my colleague Kim. Kim, the floor is yours.
So hi everybody, I'm Ekim and I'm the optical application engineer at Infinite. So I work with the optical software of Ansys. And today I'm going to present Speos to you, so Ansys Speos. Most of you already know that optics is all around you. So in your pocket you have a smartphone with a camera, and this camera gets better and better each year. You can also think of telescopes and microscopes. You can think of smartwatches which have a heartbeat sensor in them. They use optics for that. And you can think of the medical field where they use all kinds of devices to monitor what is happening in your body using light. So yeah, optics is a very wide field. And in order to simulate all those different devices, Ansys has 3 different optical software. So first we have Lumerical. In Lumerical, we simulate the propagation of light through photonic structures, so nano and microstructures. Whenever you have structures where the wavelength is about the same size as the structure itself, you work with numerical. Next, we have Ansys Emacs. We talked about it last week. This is a software to design and optimize optical components like microscopes and beam expanders and cameras. And what we are going to talk about today is Speos. Speos is the ray tracer of Ansys. It's a very powerful ray tracer. And this is to simulate the propagation of light through whole environments, so bigger environments. So we go from small up until big. So as I said, Speos is a ray tracer, and to be more precise, it is a non-sequential ray tracer, which means that light can go in all directions. It can go to the left, can to the right, up and down, as opposed to sequential ray tracing in Zemax, where light can only follow a predefined path. So people who already know Zemax know that Zemax also has non-sequential ray tracing. It has both sequential and non-sequential ray tracing. And then you might ask yourself, why would I choose Speos over Zemax non-sequential? There are a few good reasons for that. Speos works in a CAD environment, which makes it user-friendly and it is very easy to learn. It is much faster than Zemax. Of course, it depends on applications, but it can be easily 10 times faster than Zemax. It can run big models. In Zemax, you usually only model the optical devices, but in Speos, you can model the whole environment around it. In Speos, you can model environmental light, like sunlight, and this is something that you cannot easily do in Zemax non-sequential. Sometimes Zemax is still better. There are some subjects where Zemax is more useful, and that is, for example, for coherent illumination, so for coherent ray tracing. That is something that Speos cannot do. So most of the time Speos is better, but sometimes in some cases Zemax is still useful. So what are some applications of Speos? Speos can be used for light modeling, so designing and optimizing light sources. It can be used for human vision simulation, so how would a human perceive it in its environment? Optical part design, so you can think of TIR lenses, waveguides, and optical reflectors. Those kind of things can be easily designed with Speos. And you can think of machine and camera vision. So how would a machine with a camera in it perceive its environment, maybe under different weather circumstances? Or how well does a car with a LiDAR in it function under certain circumstances? So those are some nice applications of Speos. So you're looking here at a picture of a human vision simulation. So this is done with Speos. And so this is how a human would perceive its environment. But making these kinds of doing this kinds of simulation is not about making nice pictures that you can maybe show to your customer. No, it is really about predicting problems. So suppose you have designed the interior of a car. Maybe you want to see if the screens are well visible. Are there any unacceptably annoying reflections? Are the mirrors well visible? Are there maybe an annoying reflection on the windows? Those kind of things is what you're looking for. So Speos is about predicting problems and solving them. So before we go to the example of Straylight analysis, I will go more deeply into some applications of Ansys Speos, and we will start with human vision. So Speos has an accurate human vision sensor that simulates how a human would perceive its environment. So the nice thing about this sensor is that you can make changes to it. So you can change the pupil diameter of the human. You can change the age of the observer because an older person would perceive its environment different than a younger person. And as you can see here, you can connect it to VR glasses so that you can even look all around you. This is a nice example of something that is done with human vision simulation. So you are looking at the rendering of a screen in a car, and as you can see, there's a problem with it. When the sunlight shines on it, you can see that the half of the screen is not well visible anymore. This is of course a problem. And what I like so much about this figure is that they even modeled the fingerprints of a human on it to make it as accurate as possible. So what can we do about this? We can redesign the screen, and now we don't have this problem anymore. The sunlight still shines on it, but it is much better readable now. So what did they do in this case? They added nanoparticles to the screen. So in Ansys Lumerical, which we will talk about in 2 days, they determined the scattering properties of the nanoparticles, and those properties are then imported into Speos, so that you can see what the screen with nanoparticles looks like. And as you can see, it has improved drastically. Speos also has a legibility tool according to CIE standards. So it tells you how well a certain screen or text is readable. And you can make a plot of the visual performance as a function of age of the observer. So for example, if you look at this screen, a 20-year-old person can read it well, but maybe a 60 or 70-year-old person cannot read it very well. Simulating cameras. So in the last webinar, in the first webinar, we have seen how we can design and optimize a camera in Zemax, but in Speos you can go even a step further. So maybe you want to see how your camera performs in a certain environment. So you can design your camera in Zemax and then import it into Speos, and then build a model around it, like you can see here, and see how the scenery would look like on the camera. And you can do it under different circumstances. So you want to maybe compare daytime to nighttime. And as you can see, at nighttime, the face is not so well recognizable anymore. So what they did in this case is they added a lamp to it to improve the visual performance of this camera. So this is what the workflow for cameras usually looks like. As said, you start in Ansys Zemax. There you can design and optimize your lenses. Then you can import those lenses to Speos and do ray tracing in a full scenery. But it doesn't stop there. There is even more to it. In Ansys Lumerical, you can determine the quantum efficiency of the sensor. So quantum efficiency says about how well the photons are absorbed in the sensor. And then you can post-process the image considering the quantum efficiency of the lenses. So a camera with low quantum efficiency will produce these kinds of images. You see that it's quite grainy. And this is caused by the fact that the absorption of photons by a sensor is a random process. Some photons do not get absorbed. And that is why some pixels show different colors compared to other pixels, even though the illumination is uniform across the whole sensor. Another nice example is so simulating parking cameras in cars. Here you see a car with a camera at the back, and you see here some columns. Yeah, there are 7 of them, as you can see. And then with the simulation, you can determine if everything is well visible. So here you can see that only 5 of the 7 columns are visible. So you can think of redesigning the camera, and now you can see that everything is visible again. Not the top, but that's okay. You can also think about doing simulations in different weather conditions. As you can see, here are some droplets on the camera, and these droplets can hide whole objects these three columns that you see here are not visible anymore because of the droplets. So this is another example of why it can be so important to do a simulation. Even nicer example, this is a camera on a car. In these four pictures, the camera is the same, the environment is also the same, and the only difference is the exposure time or the integration time of the camera itself. So the exposure time is the time it takes for the camera to make one frame. And as you can see, the higher the exposure time is, the more blurry the water droplets get. So because of this, the camera can now see through the rain. And you want to find a trade-off, because if you have a too high exposure time, then the environment will also look blurry when the car is moving. So you want to have an exposure time that's not too low and not too high. So now that we are talking about weather conditions, maybe it's also nice to say that in Ansys Speos you can easily simulate sunlight. So you have different kinds of sunlight sources according to different standards, which all simulate environmental light. And what is nice about these light sources is that you can define a position on Earth. Say if you can choose a city, or you can choose a coordinate, and you can choose a time and date, and then the software will automatically calculate the direction of the sunlight, so you don't have to do it yourself. Stop analysis. So you can also simulate the optical performance, the structural and thermal performance of a camera. So suppose we have a camera in a car. This one works very well at 20 degrees. But as soon as sunlight starts hitting the camera will heat up and the lenses will deform. And because of that, the optical performance of the camera will deteriorate. So it will become worse. So we can just redesign the camera so that the camera works reasonably well at under certain conditions. So what you do is you design a lens in Zemax, and you can do a simulation in Speos, and you can then export these data to Ansys Mechanical. There you can do a thermal and structural analysis, import those new lenses back into Speos, and see how it would look like with the redesigned lens. With the lens that is heated up. Illumination simulations. With illumination, you can think of street lights illuminating a dark road, or the lights on the head and tail lights on a car. So you want to see if the environment is enough illuminated, and if the light sources fulfill certain standards. This is a nice example of an illumination project. So you see here the inside of a train coach, and this train coach is disinfected using UV light. So this robot walks through the alley and illuminates all the chairs. On the left, you see an unoptimized design, so you can see that the chairs in the back are not so well illuminated, and also on the side, the illumination is worse compared to the middle. And after optimizing the design, you see that the irradiance is much more uniform. So how would you diagnose problems in Speos, and how would you solve them? So suppose I have here a simple design of a dashboard with some buttons on it. You see here on the left there is a light source. The light then passes through some scattering material and then comes out of these buttons. So I can put a sensor in front of it to see how it would look like. And you can see that there is a problem. At the sides, I can see a little bit these bluish parts, and this is something that I don't want. So how can we get rid of this problem? In my sensor, I can select the problem areas, as you can see here with this rectangle, and then the software will visualize all the rays that end up there. And now I can see where the problem comes from. Some of the light rays are reflected at these chamfers here, and then they end up at the sensor. So by redesigning this dashboard, maybe by removing the chamfers or by adding some coating to it, I can get rid of these unwanted reflections. So it's very easy to do it. So now I've shown you some examples, and now we will continue with the Straylight analysis in cameras. So last time, as I said, we have designed the camera, and now suppose we can now import it into Speos and see how it would perform under non-sequential circumstances. So what is Straylight? Whenever you point the camera towards a light source, like the sun here, you often see these kinds of circles. And these circles that you see here, they are images of the lenses itself, because the light does not only pass through the camera, but it also reflects at the edges of the camera and at the surfaces of the lenses, and then ends up at the camera itself, at the sensor itself. So you can see these nice circles here, but you don't want to have too much of it because it will disturb the image, of course. So workflow usually looks like this. As said, you can design and optimize your lenses in Ansys Zemax Optics Studio. Then you can import those lenses to Speos, where you can then design the mechanical components around it, and then determine where there are some unwanted reflections, and then make some adjustments so that you can get rid of the unwanted stray light. Oh, my screen went off. Okay, so when you import the lenses from Zemax to Speos, you can do it with a so-called ODX file. The ODX file does not only import the shapes of the lenses, but also the optical properties, so the refractive index and the dispersion of these lenses. So you don't have to determine it yourself later. So this is what an import looks like in Zemax. So you just press on this button, the export button, and then an ODX file will be made. And then when you go to Speos, you can just, again, with one click on a button, you can just import the ODX file, and then, yeah, this is what it looks like. So this is how a CAD file of the lenses looks like in Speos. It's the same, but then as a CAD format. So what we first do is we want to have an accurate simulation. So the default meshing of the lenses is not enough. No, we want to have a very small mesh to accurately predict the propagation of the light through the lenses. So that's what we do first. Then what we can do in Speos is we can design the mechanical components around the lenses. So not only the lens itself, but the whole camera around it. We can do it in Speos itself, or we can import it from other CAD software. So as you can see, Speos can handle a lot of different formats, CATIA, AutoCAD, Creo, and so on, many different formats. So what we first do is we are going to do an inverse simulation. Usually light comes from outside of the camera and is then captured by the sensor, but now we are going to let the light start at the sensor itself, and then we put a sensor around the camera to see in which direction the light is going. Well, this is how it looks like. This camera shows the sensor shows the image of the sensor. That is good. This is what we want. We also around it see some noise. This is caused by internal reflections in the camera itself. But this is quite low, so this is not really a problem. But what is a problem is we see some very high hotspots, as you can see here at the corners, and we want to find out where it comes from and how we can solve it. So we are going to determine from which sequence this problem comes from. And then I first need to explain what a sequence is. A sequence is a path a light ray follows before it hits the sensor. So you can see an example of two light rays here. those two light rays follow different paths, but they all interact with the same objects, the same surfaces, before they go to the sensor. So those two rays belong to the same sequence. And here you see some different examples of sequences in this camera and the effect that it has on the sensor. So in Speos you can filter sequences. So you can just say I want to only see the light of one sequence. And all these different sequences will be ordered by the amount of energy they have on the sensor. So the highest one gets on top, and then the lower ones are on the bottom. So the first one is the sequential image. This is good. This is what you want. You want to have this as high as possible. And here on the left, you see the actions that belong to the sequence. So each action is a reflection or a transmission at a certain surface, and you can also see at which object that interaction happens. So it happens to be that sequence number 3 is the one that causes these annoying hotspots at the edges. This is what we want to get rid of. So we can select that sequence, so sequence number 3, and we can select one of these hotspots. And then we can visualize the rays. So now we can see where the problem is coming from. As you can see, the problem comes from the fact that there's a little bit of light leakage here at the stop surface. There's a little bit of light escaping here, as you can see. And now that we know where the problem is coming from, we can make some adjustments to it. Also, we want to see if there are any unwanted reflections at the mechanical parts. Interaction number 17, 45, 47, 39, and 23 are all Lambertian reflections at the at the mechanical parts of the camera. So we can now find out where they come from, and now we can make some adjustments to the design. We can also do it like this. We can just select the mechanical part and see where the reflections come from. As you can see, here's a lot of light coming from here, but also here and here a little bit. So now we can, and so now we know what we can do about it. So we go back to Zemax and we add some coatings to the surfaces of the lenses where there was a lot of reflections. And then we can import this design again back into Speos. And then what we also do is we add some absorbing coatings to the mechanical parts of the camera where there was a lot of reflections. And also what we do, we had some light leakage at the stop surface here. So what we just make it a little bit smaller so that no light can escape through it. And then finally, after we have done all of this, we can just do a direct simulation and image the sun at different angles to see if everything works well. And then we have improved our design. So that's so we have an improved signal to noise ratio. As you can see, the Straylight is much less. And yeah, so this was a quick example on how to do Straylight analysis. And we will now wrap up, and I will hand over to Tisa.
Thank you, Kim. I hope everyone enjoyed the session, but before we officially say goodbye, I would just like to share with you that in case you want to continue learning or learn more, you can visit optics.ansys.com, go to the application gallery, and there you can find different example projects and try it out yourself. Then the last but not least, there is this coming Thursday, we have our third and also last webinar of this series. You can register already by scanning the QR code you see on your screen, but if not, no worries, because you will receive the registration link in the email, including the presentation slides and the recording. So, however, you are very welcome to join us on Thursday again. Till then, yeah, I hope you all enjoy the day, and I see you in 2 days. Thank you.
Yeah. Bye bye.
Bye.